Hello everyone, it's June 12th. Trying to analyze the data a little bit more for my study, for my research, but I just have a lot of trouble figuring out what exactly to analyze at this point. I want to do some case study, but I have no idea like how the case study should proceed. So that's really difficult to figure out. Alright, anyway, so I'm gonna do this today, and we are going to do this again, and I'm trying to use the lazy. Alright, I'm trying to use the lazy and see if lazy can get us pass. If lazy still fails, then we have to check the result. Well, we check the hint first. Anyway, equal row and column pairs. Given an n by n matrix, return the number of pairs R and C such that row and column are equal. Equal if they contain the same elements in the same order. So it's 277, 277, right? Yeah. That is an interesting question. 0, 0, oof. So basically you have to go through, ooh, hold a second. N is 200. So you go through every single thing and then try to see if this and this is equal. This and this is equal. Yeah, because there are only 200 rows and 200 columns. You can just go one by one. Right? You just go one by one. I mean, we can turn everything into, I don't know, what you want to turn it into a string. And we can compare string. We don't even need to compare string. We put all the row string into a set, all the column string into a set, right? And then we just go for each row. We try to find if in a column string there is anything. And I think a row and a column. How about a column and a row? If they contain the same amount. Hold on. So 0, 0 is considered 1. 2, 2 considered 1. 3, 2. The third row and the second column. 0, 1, 2, 3 in the second column. Okay, yeah, so for each row index, now string, you can check on a column to see if there's anyone matching. Ooh, it may be multiple matching. But 10 to the 5th, if it's 200, 200 times 10 to the 5th, that's a gigantic, right? That's a gigantic string if you want to use string. Is there any other way? I mean, we have to go through every single pair, right? And then at every single pair, how can we make the comparison faster? Or some pre-computation to make it faster. I don't know. It might. I don't know. Let's see. Let's say. Okay, this is the largest, right? And I say str s is equal to, let's say, full for this in range 200, right? And then we want to join this, right? So we can say this dot join this, and then columns, let's say, equals s for this in range 200. That is This is a row. This is a column. I have 200, so we put them together and then get a row. And then the row will be the same. All right, let's see. Will this causing memory issue? Oh, my bad, str. Will this cause memory issue? Wait, what was this? Just have to return the value. I guess it's fine. All right, then we just turn everything into a string then. All right, so rows, collections. Let's do counter, okay? And then for row in grid, each row, I can say this dot join for seeing row, selling row, strc, right? And then is for each row we have this, and then we say row counter equals counter of this, okay? And then for each column, okay, for each column, then we just find how many counters there are, right? So rest equal to 0. And for each column, so we say for j in range n, okay? So column str shall equal to this dot join str grid I j for I in range n, right? And then rest plus equal to row counter column, and then we'll return rest. Let's see. Equal. Huh? That was terrible. It's a terrible take. What the hell? Hold on. What went wrong? For each column, I find out. Hold on. Let me see. Row counter 321 176 277. That is correct. And print column str. Alright, something is not right. What the hell is this? Generator object. Wait, what? Oh gosh. My bad. I put the parentheses on the wrong thing. Alright, just let's see if it's gonna time out. Hopefully it's not. Hopefully it's not timing out. It's not timing out, so I guess that is the way. I was a little bit worried. turn each row and column into string and match string using counter. O(n) squared. Brute force hash. Oh, tuple. Holy crap, you can use try. You can use tuple. Maybe tuple is better. Why didn't I think about tuple? Tuple. Match tuple. How do you do tuple? This is tuple. We'll do tuple. And then this is just going to be... Yeah, I didn't think about tuple. Kind of stupid. Tuple might be faster. I'm not sure. Not sure if tuple is faster. Is tuple faster? Oh, that's not str. Yeah, slightly faster than string. Alright, so the actual one is try. How do you do try? For each row. Oh yeah, you can do try. You can. For each... We can create a try for each row. Wait, hold on. Create a try for each row? Yes, create a try for each row. And then given a column. And then we column start from the first one. And we try to match. Try to match. See if we match. Oh, do we want to do this? Yes. Let's practice try. And think about try at all.
Where was that?
Use try. Okay, root. No, try. Default dict. I haven't done try for a while, so lambda. If I remember correctly, this is no. Try is lambda. Default dict try. That's the try. Okay, so we're gonna build a try for each. Right, so root equals, so we're gonna build try, okay? Build try from all the rows. Okay, so root equals to try, right? And then we're just gonna say for row in grid, node equal to root, right? Okay, we start from root, and for C in row, and we say node equals node C, right? And then at the end, I'll say node star equal to true. Doesn't matter, we just need to notify at the end we have it's over, right? It's over. And in fact, we don't really need, because you can keep matching to the end, because n equal to n, so we don't even need this. Okay, so I'll build a try, and then match columns to try. Okay, so for j in range n, Okay, so node equal to root as well. Then I'm gonna say for I in range n, every value we try to say if grid ij is in node equal to node grid ij, else break, else, oh, hold a second, you need to count node star equal to node get star 0 plus 1. Yeah, so this is the counter, right? This is count the number of rows ending in the same node. And then else, which means we match every single one. So I say rest plus equal to node star dot get, just in case, dot get star 0. Turn rest. All right, let's see if this one's right. N is not defined. Of course it's not defined. We haven't defined it. Try seems to be working as well. Okay, so let's try. What's the time complexity of try? I mean, this is O(n) squared, right? O(n) squared. Yeah, it's an O(n) squared because everything to build this is O(n) squared as well, right? You build this in the O(n) squared, you build this as, I think it's O(n) squared. So there's nothing to try. But you need to keep count. Exactly, you need to keep count. Is this my browser? Alright, so this one is done. Okay, I'm gonna go here. Let's do the. I was trying last night after I finished, but yeah, it's not ready yet. Okay, update. We have a lazy. Right, we have a lazy. Now, if we have a lazy, that means, dear God. I think we should do default dict, honestly. We should do default dict lambda math.inf. Okay. And then all we need to say is if this index is smaller than math.inf, that means we have something that's lazy. So we set the tree, right? We set the tree. And after we set the tree, what do? We have to propagate, right, to the next. So we do the propagation. Okay. We do the propagation to the children, and then it's the same value to the children. And of course, this shouldn't be, because I shall be minimum of self.tree index and the value, right? We'll do that. And then after that, self.lazy, we need to reset to math.inf. We'll reset it. Index. Right? And now we do this and apply. Yeah, so this is to apply whatever is lazy, so it's the previous, right? Something that happens previously, we haven't propagated to the current yet. So when that happens, we keep the same value. But now what we want to do is to change. Actually, this is not val, dude. It's you want to propagate lazy, right? That's what to propagate. Or use self.lazy, whatever is on the lazy. And this is going to be the value. Put the lazy value there. Right? Because the lazy value has been, input. And then here, this is going to be the value. And this is going to be the minimum self.tree index and the value. So we do whatever, right? We do whatever the lazy value first, and then we update the current value, right? Else we do this. This is fine. Oh, we have to also. God, Lord. I think I have to do this one for every single one of them. Because otherwise you will lose value. Okay, so we do that. Alright, and of course here is going to be the current value. Here is going to be the current value. We put it to the next. Alright, we put it to the next lazy. Right? The next level of lazy. Otherwise you do, the same thing. And for here it's just going to be value. So that's fine. But we have to update the lazy. Okay, how about query? Query, of course, we have lazy first. So it's exactly the same, right? If this position we have a lazy, right? If this position we have a lazy, we have to first use the lazy, right? We first use the lazy to update the current value. And once we update it, then will be pretty much the same. Okay, so with this chain, let's see if it still works. Still works. Now it's the question of whether. So this is a lazy. Yeah, let's change its name. Lazy mean seg tree. Do I have confidence it will work? No, I do not. Absolutely not. Come on. Absolutely not. But so 3,613 milliseconds. If it doesn't go down to like cutting half, I think it's not worth doing it. No, that's not worth doing it. I don't think so. It's still gonna. It's not a lazy tree, man. It's not. It's not a lazy tree. We put it in up there and then just say, yeah, it's not working either. So we have to be smarter then. In fact, I think this one's even slower than what we had before, because we have the lazy part. So it's not lazy. Okay, so lazy doesn't work. Not lazy doesn't work. So we need to be smarter. Yeah, this one doesn't even hit. It doesn't even hit the one that we want. It's actually slower. Alright, we're gonna go for the hints. So we tried as best as we can. So the lazy actually have to also go the non-lazy. I wanna order some. I want this one as well. Yeah, 40. So yeah, this is actually slower. So Let's do this. Lazy segment tree. Actually, we can just do a main segment tree. That should be fine. Okay. So here's solution 1. This is just using segment tree. And then we need a solution 2. Right? Using lazy segment tree. It's actually slower. All right, time to hint. All right, what's the hint? Binary search, binary index. How can you do binary index tree on this? Maybe you can. Segment tree, UnionFind. What the hell? All right. Keep track of a priority queue that stores distance ik for all k smaller or equal to j. And another product stores. Wait, priority queue. Wait, what are we doing here? That store this to calculate this ij. So from ij. Wait, so the minimum number of steps to reach ij. Okay, so not from ij, but I think it's the same. So okay. So a minimum number to reach ij. That's fine. It's the same row every k. So the distance and I and k, a priority queue, and another priority queue that stores that. What does the priority queue do for us? You have the distance. Okay, I give it to you. You have the distance. And then what? And then you have the I, and then you have the k. So if priority queue, the distance goes first, right? And then you have to check for I, right? Ooh, you check for I. If you go top to bottom, right? If you go top to bottom, and every time you want to do this, now the distance, the smallest the distance comes up first, but that could be from a different I, right? That could be from a different I. But if we're just talking about the current row, okay? If we're just talking about the current row, if we're just talking about the current row, then you just need, that's still, you can't just do the current row if you want to find the, I mean, I don't like to find the minimum to reach, and I still like to think this way, right? So if you go here, if I keep a priority queue of what we have encountered before, then what are you saying? We do 2 rounds. 1 round specifically on a row. Nah, that's not right. We have to do both. But anyway, what they're trying to say is we have priority queue. Okay, so instead of a segment tree, we have priority queue for each row. So out of this row, we have a priority queue. And then for this priority queue, but still for this priority queue, or they say just 1 priority queue where we have I and K. But that doesn't make any sense. Right? How does that make any sense? Keep track of priority queue that stores this for all k smaller or equal to j. So we have all these values. So we have the smallest value with the current I. But that's not what we want. Because we have to also consider this. Oh, this hint is, I don't know. I didn't quite understand what the hint is trying to say. How does priority queue work in this case? It doesn't. All right, let's check. Oh my God. BFS DSU, oh my. That's very different. Yeah, I try segment tree. Sorted list. My God, sorted list again. How do you use sorted list for this? Wait, what do we want? We want, geez, I didn't think about sorted list. We want to find the smallest value in a range. Enjoy. Oh, in a range. In a range. I mean, sorted list, we can put indices, right? And we can do I, is that what you're trying to say? Do I range? Hold on. Sorted list, does it have an API for this? Here. Sorted list, remove pop, we can bisect, index. No, I want I range to find a minimum. Let's check. I don't know. Oh, hold on, this is different. Maintain a queue to determine which cell to go to next. This is Dijkstra. God, using this to keep track of visited nodes. That was exactly the same thing as last week's hard problem. You know which positions are open, and you go through them, right? And then you remove. Use iRange. It's used iRange again. The second time iRange. Okay, I gotta take a look. So we start from, oh, it's just a regular BFS, right? Holy crap, it's a regular BFS. It's not even DP. Okay, so this is the position, and this. Right, and then we pop them out. If this, we're done. Otherwise, S0. What the hell is S0? All the positions you can go on a row. All the positions you can go on a column. Huh. Wait, hold on, let me think again. Range M. So that's all the rows. In each row we have these positions. Okay, yeah, this is all the positions on a row. This is all the position on a column. And then this is the range that I can go from this to this. Yeah, range, and I think iRange is inclusive. I think it's inclusive. Yes, inclusive. So inclusive, so these are the positions you can go on a row. And then you, oh my goodness. All right. You remove this position and you remove the position on here as well. Okay. I see what this one is doing. Yeah, this feels Dijkstra to me. Yep. Okay, we're gonna Dijkstra this then. Test case a week. Wait, really? You cannot use Dijkstra, huh? What is it trying to do? This is this. So this is the distance. And then it starts to pop it out and then push it in. It has a distance, yes, this is Dijkstra. If it's larger than, we'll reset and then push it back in. And we have to handle rows and columns, right? Yeah, I mean, it's correct to say this is no different because as you go, the distance always increases. Even if it's a regular queue, right? Even if it's a regular queue, the distance always increases, so there's no benefit. Hold on. Sweep line. I forgot about sweep line. Okay, so I'll do this. Man, there's so many solutions to go through, man. Skip ahead. Segment tree doesn't work for me. Yeah, sec tree is 2, doesn't work. DSU. DSU? Is this one right? Oh, Jesus. To connect, Use DSU to keep track the next point, which is not in the same. I have no idea what he's trying to say. So all the rows, each column is a UnionFind. And then just the regular. So basically what they're trying to say, all they're trying to do is BFS without revisiting. Because at each position, you might revisit the previous. I don't understand. What is the pain point for BFS? You have many positions to go, I know. Right? So you go to the next position, you have many other positions to go. Okay. So, yeah, you want to know whether this position has been visited before. So you want to only do MN. But it's very difficult to know if any position has been visited before. But why cannot you use a set to determine if a position has been visited before? In a certain position, you can go row. Okay, I go row. Every time I go, I put it into a set saying this has been visited. This has been visited. And then you go down, right? Do the same thing. So all of these has been visited. And that's the first time you visit them, right? And then what? And then the next one. I like why they have so much trouble get rid of the position that you're visited. How can we find the next unused point? Why set doesn't work? I mean, you already use a set. You already use it, right? Right, you set it to this. That means this position has been visited before. And then when you try to go for the next one, you just don't go there. Shit, did I miss something? You're starting from here, right? And this is position 1. And then you go here. Here. These are 2. You set them already. And then you go here. And then you want to go this, but this one is already visited, so you don't visit this anymore. Oh, that's the problem. The problem is you cannot keep going. You go this again. Ah, I see. Now I see. Yep, you want to reduce the choices. There are just too many choices. From every position, you have to choose. You have to go through everything. That's why set doesn't work. That's why sorted list works, right? Because at each position, you can find within this row what are the indices left that you can do, right? That's the benefit of sorted list. Use iRange, and then whatever rest you can choose, and then whichever you use, you delete. I see now. Okay, so now back to UnionFind. Now we know this is sorted list. That's not. No, that's a different problem, sorted list. Yeah, it's a different problem, sorted list. This is the AVL. This is the AVL. We didn't do the AVL yet. Hold on. Line sweep. Oh yeah, this line sweep. Dude. Okay. Well, take a look at line sweep as well. Second tree most likely is not going to work. What's this UnionFind then? Okay, so I think what he's trying to do is... Oh, I think I know what he's trying to do. Union, every position, everything you visited, you union them together for a row, right? Then the next position to visit. So if you set the parent to the largest index, then the one you visit is gonna be root plus 1. So the case is you want to merge the two, and you want to point to the parent. You want to point to who should be the parent. You want to keep it to be the big one. Yeah, you always want to point to the big one. It has nothing to do with rank. This one has nothing to do with the rank, because you want the parent to always point to the largest index. So the next time when you come out, you just do this. Holy crap, this is good. My God. Yeah. So you do this, right? While this is smaller, then this is the maximum you can reach, right? And this is the current on the current row, right? On the current row, what is the index, right? The next one you can do, and whatever it is, you say the current row to find C. This is the column value, right? Your J. So you're trying to see what is the earliest you can do. It can either be yourself, yes, or it's gonna be the next one you want to visit. It's gonna be +1. Oh, dude, Lord, this is good. Okay, so we have three methods to go through. Jeez, man. Okay, I don't have Ghana to do it today, but yeah, we'll do this tomorrow. Yeah, I do think, I don't know, if it's a medium problem, I don't know. Every time segment tree is there, I don't think it's a medium problem, because segment tree is always, convoluted to implement. So I do think they shall allow segment tree, but that's a different question. Sorted list is always, I'm a little bit iffy about sorted list every time, because in the interview I don't think you can use sorted list. There's no way. Man, this is a contest, so it doesn't count. Contest, sorted list, it's all fair game. But in reality, I take it back. In reality, you can use sorted list. All right, you're doing whatever project, you're not using sorted list. Of course, you can use it. But in the interview, I have been through an interview where I want to use sorted list, but I can't, because there are other solutions. I mean, in this, at least we have two, right? These two, they both claim. I mean, we've done this already, so I know this is very fast. This one should be very fast. And this, I forgot what line sweep is. You know what? I might know, but we have to read through this. So there are methods without having to go through sorted list. So we're gonna do that. In fact, we're gonna do all three. All right, we'll do all three. So, all right, we'll do this tomorrow. I'll see you guys tomorrow.